Thank you. Glad to be being here. So the Riemann solver, today I'm going to talk about the Riemann solver and their applications. The Riemann solver are popular in hydrodynamics, especially in the grid-based hydrodynamics. And I'm going to show how to solve the Euler equations together with an equation of state with Riemann solver. And I will apply them to solve the light curve. Give an example of the light curve of a variable star, which is a kind of asymptotic giant branch star. So the first, let's start with the hydrodynamic approximation. Hydrodynamic approximation assumes that matters are continuous and individual particle cannot be seen or felt by the system, and we then apply conservation law, which include mass, linear momentum, and the total energy conservation. Then we reach the Euler equations. This set of equations includes some source terms, and they are additional source terms. The equation in black color, they are the original inviscid Euler equations. And equation number 4 lists the total energy. Well, it has a specific internal energy there. This specific internal energy is usually assumed by a perfect, supplied by a perfect gas equation of state in most prevalent research, because with this type of equation of state, you can, this is also called gamma law, gas law. With this type of equation of state, there is a beautiful procedure to solve this Euler equations with Riemann solver. However, in reality, the realistic gas is far from this perfect gas equation of state. Next slide, I will show what is the difference. So this is an equation of state that has of hydrogen is 70%, and the other 30% is helium. So the curved line shows the specific internal energy of realistic gas. And the solid, just the linear relation, shows the gamma law equation of state, specific energy. I assume that the mean atomic weight, is 1.3. The first jump, the first jump there is the dissociation of molecular hydrogen, and the second jump is the ionization. So you can see the difference is quite dramatic here. Since this is in log, so at some point it can be as big as 1 order of magnitude in internal energy. So therefore, if you only use the perfect gas, the gamma law gas, to approximate a realistic problem, to solve a realistic problem, there might be some issue. You don't see, you will miss a lot of physics.
So this assumes that you converge to an equilibrium. What are the typical time scales?
Yeah, that's a good question. So I think all the hydrodynamic approximation, they assume local thermal equilibrium. If there is no, the Euler equations itself become questionable. If there is non-thermal.
So for example, if you're in a situation where if the timescales for this transition are too long, you can just assume then you can just assume that this transition doesn't happen. Doesn't invalidate the hydrodynamic equations.
But it will change the energy budget.
If you don't, right? If the timescale for producing, for example.
Well, so that's okay. We get the point. Go ahead.
Yeah. What is the Riemann problem? It's an initial problem, initial value problem that has a single discontinuity. So it's, for example, its left state and the right state has different initial value, and it's separated by x equals 0. This discontinuity usually will cause a lot of problem in hyperbolic system. For example, let's start with conservation law. Conservation law, which is what Euler equation is, the conservation law of scalar system. If this A is a constant, is any constant, then the conservation law of equation 7 can be written in equation 8, and then it has a exact solution if the initial state is given. And this A is called the speed of characteristic. This is for scalar system. However, if you study the nonlinear system, this shows the Burger's equation. It has the U grad U term. So if there is any initial state is U at time equals 0 equals V, and we use this initial state, you will find the characteristic line is like such. Then at time 1 equal 1.5 or 1.6, the characteristic lines, they intersect. This poses challenge because when they intersect, the Riemann solver is in trouble, and that's where shock forms. The linear theory doesn't have solution to this kind of intersecting characteristic line. So we need to use the nonlinear theory. In general, we use the Jacobian to approximate the conservation law PDE. If we have a conservation law of this type, and we use grad flux to be, we call it the Jacobian of flux F, then we study the character, how does the Jacobian behave to classify the type of the PDE. A real look of the Jacobian of the Euler equation is listed in equation 16. This has, I don't assume any specific type of equation of state. So actually the A is the sound speed here, A is sound speed here, H is the enthalpy, and P epsilon is specific energy, internal energy. So for perfect gas, there is an explicit expression for all these three quantities. However, for a general equation of state or any equation of state that has implicit relation, this Jacobian will be formidable. And what I'm going to do is to solve this type of equations. This is an example of the pure hydrogen adiabatic sound speed. This is in log, the color is in log shape, logarithmic scale. So you can see this is the first phase transition. This is the second phase transition. They have, this adiabatic sound speed is quite complicated. You don't get a monotone behavior. So since the Jacobian of Euler equation in 1D, it's a 3x3 matrix, we would think that it has three waves. Actually, that's the Riemann solver. What the Riemann solvers, they are Riemann solver constituents. One is the middle wave, and the other is the nonlinear wave. The middle wave is also called the contact discontinuity, which is colored in red. This plot shows a rightward shock wave, which consists of a left rarefaction wave on its left-hand side and a shock front on the right-hand side. if there's some mathematical background, what Jacobian can be used, can be applied the Riemann invariance. It requires the Jacobian to be diagonalizable, and then its eigenvalue must all be real. And so after that, we can apply the Riemann invariance. This is a key tool that we use to assemble the Riemann problem solution. So we apply the Riemann invariance to the contact discontinuity with any general equation of state, and we can get the jump condition. The jump condition from the left to the right of the discontinuity is dp equals 0, du equals 0. U is the velocity, p is pressure. And we also apply it to the left or right nonlinear wave, because there are 3 waves. We apply it to the nonlinear wave, we get this to ODE. This is a relation of pressure and u. And we can see that the velocity u might increase or decrease. So that poses trouble when it reduced to the kind like the Burger's equation. If the wave speed of the behind wave speed is catching up the front, is going to form a shock. And this solution will not hold always. So we need to solve another kind of equation called Rankine-Hugoniot relation. This is an illustration of shock. So this is the pre-shocked gas, and this is a shock that traveling at the speed of lambda, and this is a post-shock. It has a relation that holds everywhere in a fluid, and that's relate the pre-shock to post-shock relation to their state. And J is the flux across the shock, and then you got 3 equations, and additionally 1 relation, and another equation of state. But you also have 5 unknown, which is this 4 and the J. So 5 equations, 5 unknowns. Then, we need to solve. Also, anyway, this equation 21 gives a relation of the P and the U, which is pressure and the velocity. This is a relation. On the previous slide, we also give a relation of the pressure and velocity. So if we put these 2 quantities on one plot, there is a phase plot called PU phase plot. This phase plot is very clear. There is its left branch, which is the left state if you start from the left state, and the right is the right state. They intersect at one point. This point has a single velocity of u and p. Remember that the red line is the contact discontinuity. We solve that, and we say that the jump condition is dp equals 0, du equals 0. So this intersection is actually the solution of the Riemann solver. The whole theory of Riemann solver is to find that point with equation of state. But as you see in those Rankine-Hugoniot relation and also the nonlinear wave, they all have, you need to solve the relation of epsilon, the internal energy, pressure, and density, also the sound speed. That means you need to solve the equation of state when solving the Euler equations. So that means you need to interpolate. You can interpolate a table to find the relation between P density, pressure density, and internal energy, specific internal energy, or sound speed. Like this, you interpolate the table. but the table could be very, very large because the transition there is very sharp. You need to put a lot of density resolution there to get an accurate number. So I implemented the tabulated method, but on the other hand, I tried another method called analytic way. So I calculate their sound speed, adiabatic sound speed, and the pressure internal energy relation in the runtime. The technique is to divide the state into 7 states. So you estimate the states, these states illustrate some phase transition. So in each state, you need to solve in these 3 states, you need to solve algebraic equations. For others, you don't. Hi. This is an example of pure hydrogen. Yeah. Pure hydrogen has ionization, and it also has the dissociation from molecular to atomic. So there are 2 phase transitions in here, which correspond to 2 giant, huge change in the internal energy.
So this gets back a little bit to Amal's question, because H2 molecular hydrogen formation is a slow process of low densities.
Mm-hmm.
So it sounds as though you're assuming that that's a rapid process in order to do the calculations. Are you only concentrating on high densities where three-body processes will make that fast?
I think you are referring to something of process, the actual reaction process, the rate. So that's, yeah, I'm assuming the rate is immediate. You can form whatever. It's only thermal balance. You can form when thermal balance is reached. Yeah. So I calculate on the runtime. Yeah. The only requirement for the equation of state is 24 and 25. They are proven on some mathematical journal, and I showed that if your pressure satisfied this 26 to 27 relation, and your specific internal energy satisfy 28 to 29, then the equation, the Riemann solver also hold. I think these 4 relations are more understandable in terms of ideal gas, because ideal gas, the pressure increase as density or temperature increase. Yeah, and almost gas should satisfy that.
Is this required for the stability of your integrator?
No, this is a requirement for a single solution of the pressure of this point. A single solution. If this sufficient condition is not satisfied, because this is a sufficient but not necessary condition, so that means maybe some stricter condition will also apply, but I haven't. Yeah. I haven't checked if the degenerate gas also satisfy this, but if anyone knows, that would be great. Then we can apply the equation Riemann solver to real problem. This is a solid shock tube-like problem. The Riemann solver, we implemented 3 Riemann solver, and the solid line shows the exact solution, and the red dots shows the HLC plus analytic EOS solver, equation of state solver, and the blue dots shows the HLC plus tabulated equation of state solver. HLC means is a type of approximate Riemann solver, that it's approximate Riemann solver, which is popular in computational astrophysics. Yeah. The first panel shows the density, and this three shows the concentration of hydrogen. The equation of state I use in this test is the pure hydrogen. We can see that the approximate solver matches the exact solver quite well. And this is a two-shock test. It's partially ionized. It's partially ionized. 0.5 means almost 50%. And that's posing some question. There is some issue in solving the partially ionized gas in the HLC. We are still investigating that. This is showing two rarefaction wave. The gas is leaving the center symmetrically, and this heating, this is the temperature. This heating exists in all the grid-based code, I think, and it's not a problem of the Riemann solver itself.
So
Please.
what application are you thinking of?
I haven't got to the application. In 2D, if I apply the equation of state to the 2D problem, it shows a fireball that expanding into an ambient medium, and it has a compressed shell. In the meantime, if I use a gamma law gas law, which is 5/3, gamma equal 5/3, at the same time their structure is very different. However, the realistic gas is somewhat similar to the gamma equal 1.1, which is shown on the third column. But they are still different in size. As you can see, that one expands larger.
So we would expect the low gamma to be more concentrated, to be emptier at the center and more concentrated toward the edges. Because what I'm seeing here is I'm having a hard time because you expect more material to be concentrated towards the short front.
Yeah, compressibility. This is about compressibility. The ideal gas compressibility of perfect gas depends on gamma, and the realistic gas has higher compressibility. That's why you can see a compressed shock. Then this slide shows the hydrogen concentration of each species of that shock expansion. This is the molecular hydrogen. At center is 0. The white is 0 because it's high temperature, high density. And the outside, this is ionized. No, sorry. I got it wrong. This part is, the center is, this is the, this is the ionized hydrogen. The center is yellow, and means that it's fully ionized. But the surrounding is, there's no ionized hydrogen because it's low temperature. And as the fireball expands, the atomic hydrogen appear. But the cooling wave is traveling inward. At this time, it hasn't come to the inside. But gradually it will recombine, and the atomic phase shows up.
But this is an adiabatic simulation, right?
Yeah, it's adiabatic. There's no
Cooling wave, you mean just adiabatic?
adiabatic expansion. There's no radiation cooling or that kind of thing. But yeah. Well, I'm going to apply this equation of state Riemann solver to the giant star, AGB, asymptotic giant branch star. Asymptotic giant branch star can be illustrated in a HR diagram with this. This is a branch, AGB branch, and this is showing an initial mass of 2 solar mass evolution. So the variable star has light variation in their light curve, and its bolometric variability is roughly 0.4. This figure shows a mirror light curve. You can see the optical band vary by like 5 magnitude, but that's not the main flux of this bolometric luminosity. If you go to like more redder, its magnitude changes smaller. The main flux in mirror-like object is in the far infrared. So the bolometric is not several order of magnitude. We need to study to simulate set up the AGB model. We need to understand the structure of the AGB star. From the inside, it has a carbon or oxygen degenerate core, and as we move out, it has the same.
What's the source of the AGB star's variability?
The source? You mean observational source?
Oh, no, just what's causing it to vary by orders of magnitude?
We think it's the pulsation that causes its variability. It's pulsation in the convective zone, and then it pushes out as the shell expand or shrink. Yeah, good question.
Oh, that's
5 magnitude. Yeah, 5 magnitude. It's correspond to like 1,000 time change. So from inside out to outside, it will finally meet the ISM, which is at 10,000 stellar radii. We use MESA code to simulate the inside, the core, and the convective envelope. Our goal is to start from the pulsation layer, and we simulate the shock generation, and we add dust, and then we see wind acceleration and up to the stable outflow.
How does the sound crossing time of the envelope compare to the pulsation time?
Sound crossing time to pulsation time. I think you should compare you might compare the pulsation time period to the free fall time scale. Sound crossing time is roughly several hundred days. Yeah. There are 3 characteristic number of the pulsation. We model the pulsation like a piston. So we put a layer in 1D model. We put a layer of piston at the stellar boundary, and we set its amplitude, its period, and location. These 3 numbers are actually not clear to us, and they are very subtle. But once we assume the location, from MESA code we can get its temperature and density. And the other thing we need to add is the dust formation. Dust form, we assume that dust form is at around 12,000 Kelvin, which is around the dissociation of the hydrogen. That's why the hydrogen is important. And we also consider radiative transfer. In MESA code, if we start with a 1.5 solar mass star with initial metallicity of 0.02, then when it reaches 1.02 solar mass, it is marked with a red star. It has a luminosity and radius listed on top of the figure. We are using this model. We are using this model as an example to show that the pulsation-driven wind, the pulsation and dust-driven wind, can generate some light curve difference. So in profile, this model looks like the black solid line. We choose two positions to put our piston. One is the minimum density point. At this point, its temperature is only 7,700. Actually, the hydrogen is almost recombined at this point. We also put another point to the piston, radii to the piston, which is slightly inward, 5 solar radii inward, and that's 8,700. So the difference is that at 8,800 Kelvin, the hydrogen ionization is much different. And they will make a big difference when we drive the wind out, drive the pulsation out, and the gas will cool to release the photon, and we can see the light curve is very different. If you use a perfect gas, this difference of temperature only means 10% of the internal energy budget difference. But the realistic gas can have 3 or 4 times difference. Usually, the motivation of this research is that the luminosity variation is usually modeled as a free parameter in stellar evolution code. The wind code, the wind generation code. But with realistic equation of state gas, we can relate from the core to the outside of the wind, and we can relate the pulsation to the luminosity variation. And we are solving this set of equations. We consider the radiation force and the gravitational force. Also, we consider cooling. The cooling is calculated by line cooling and molecular cooling. I haven't implemented the heating terms, which will actually do some. It's actually very important here, but I haven't implemented it. I will analyze it later. So the result, the light curve, will look like this. The dashed line is, you look at the left axis. The dashed line is the black body part of the, yeah?
You said for your initial calculations, everything was in thermal balance, but now you're adding heating and cooling.
Yeah, they are optically thin cooling.
Okay, so but is everything still in equilibrium? Is the sum equal to 0 still?
That is, I think, yeah, that's a question. I don't know if the optically thin cooling means non-equilibrium. They are non-thermal, but how much they will change the thermal equilibrium, that's a question. Yeah.
Are you tracking photons as well?
Yeah.
So you have the radiated flux.
Flux from inside out. But although the star has a size, I'm treating it as a point source. The star should, you should see the solid angle difference of the star if you are close to the star. But I'm treating it as a point source. So the black body part, which is from the mesa, is shown as the black dashed line. This red line is the piston pulsation amplitude, the phase. I'm showing here to show the phase of the piston.
If the radius of the star changes, so how does the velocity remain constant?
It's not. I'm not changing the radius of the star. You don't think. I don't think in a Lagrangian way. It's an Eulerian frame. So I'm only changing the piston, the velocity, directional velocity of the piston. It will make the envelope, the photosphere, expand or shrink. But wait a minute. Yeah, it will. But
Is the piston the internal convection on the envelope or something? Or I think we're just trying to understand exactly what.
in 1D, the convection, usually they model it as the mixing length. But here it's evolving on a dynamical time scale. At the photosphere, it's on dynamical time scale. The mixing length theory may not be very useful.
It actually gives you small variation, right? So it doesn't give you environment changes.
In reality, the giant star is not a sphere. It's not a perfect sphere. It should eject blobs of hot gas at some direction at some point. So actually, the 1D model is only a crude approximation. If you are talking about that, then the convection is driving, overshooting blobs into.
Beetlejuice and we have stuff like Myra, right? And
Yeah.
they have bow shocks, and the bow shocks are spherical. Right?
Maybe we can talk later. Yeah, we definitely need to talk later.
You have an envelope, the envelope expands, at some point you have a combination, and then the pressure drops, and then it starts falling again, and you have the cycle, and then it heats up.
Yeah,
and
yeah.
This is what's driving it. I think it's convection.
Yeah. So here I'm not considering the expansion of the photosphere or shrinking of the photosphere because the energy from the nuclear to its envelope, this in this lens, is nuclear. All this energy is from its nuclear, right?
But the optical depth changes, so the diffusion time changes.
Yeah.
So on average you get the same luminosity, but instantaneously you can have different luminosity.
Yeah, that means you need to actually resolve the optical depth very accurately. That's a very good point. This is still an ongoing research. So I will take your advice. Thanks. So this lines, this blue line and green, yellow, they show the cooling. They actually show the additional cooling from the gas, the hot gas that's coming out of the photosphere. We are tracking the gas that's cooling outside the photosphere. So the blue line shows the real gas, and yellow is gamma equal 5/3, and yellow is 1.4, and green dots shows 1.67. You can see the difference is not big because, as I said, at this point the recombination is already happened. So you would expect they are not making much difference. However, the next slide I will show these blue dots remain there, but I will show the piston that I moved a little bit inward. So this is the cooling of the gas. That's if I move 5 stellar radii inward, and they are quite different from the gas that they are both realistic gas. They're quite different because of the energy budget is very different.
What's the vertical axis for the stars? Is those velocities?
This is showing the phase of the piston, and this is the velocity in km per centimeter.
But
That's per second,
when
but
you see a star,
yeah.
see a star like the red stars.
Yeah.
Is that refer to a velocity value or a luminosity value?
A luminosity value. Light curve means luminosity.
Oh, I see.
I don't think.
jumping up and down.
That's a very good question, because the source term, this source term I use, this is a very stiff function. This is a very stiff function. When it reaches the, it's very sensitive to the density. When the shock reaches the optically thick region, then the optically thin cooling suddenly is just turned off. And then when it, yeah, so I can only apply the optically thin cooling when it's optically thin. So when a shock is there and the density rises. As it rises, the cooling scale as rho to the 2. Then, but when it reaches the optical thick region, it suddenly drops because it's optical. I turned off the optical thin cooling. Then again, as it expand again, it rises again, but then it drop again. So you can see that as the pulsation goes from the bottom to its maximum, is on this half phase, the luminosity increase. But when the piston is speed from its maximum to the inward maximum, the luminosity drop to very small. If I have heating, I didn't add heating, but if I add heating, you will see the dip below the black body. In terms of mass loss rate, the realistic gas is similar to the 5/3 because they are almost recombined at that point. I didn't show the one that has a deeper piston because that need a different piston setup, like the amplitude and the period, because the time scale there is intrinsically different from here. So this is in unit of mass loss, solar mass per year. A typical AGB star has solar mass loss rate of 10 to the minus 8 to 10 to the minus 5. And here is showing 10 to the minus 7 and up to 10 to the minus 6.
So you do not have radiation pressure on dust.
I have. I don't have. What I'm missing is the energy transfer from radiation to dust. Yeah, if you absorb, if dust really.
Radiated energy exchange.
The dust will absorb radiation, and it will take it momentum and energy. I'm taking it momentum, but I'm not taking it energy.
You do not bring the thermodynamic coupling of dust to the gas.
Yeah. The dust formation is I assume that the dust form when the gas temperature drop below 12,000 K. Yeah, but its equilibrium with radiation is also important, and actually that's very relevant to the size of. You need to resolve the size of the star. You don't treat the star as a point source anymore, because the solid angle make a difference. Because the dust form close to the star.
But there will also be energy exchange between the dust and the gas.
Yeah. Dust and gas, they exchange energy via friction, exchange some energy.
Well, not just friction, there are different temperatures, right? The radiation heats the dust.
Yeah. Sure. Dust will also radiate. They absorb radiation, they also radiate.
You said you're not calculating that.
Well, I'm not. Yeah, I'm not
calculating
calculating the energy equilibrium of dust. some recent calculation I show is that the cooling and the heating of dust, they are both very large. This number, they are also all very large. And if you just consider one of them, and you compare it to its internal energy, the time scale would be like seconds, on the time scale of seconds. But because they balance each other, if you consider both, their time scale will become days or several hundred of days. So you need to really calculate, use the ray tracing, non-local ray tracing to calculate the dust formation. To summary, we have described the exact general equation of state Riemann solver that can solve the Euler equation and an equation of state together, and also the HLC type of equation of state Riemann solver still have issue with the gas when it's in the middle of phase transition, but overall it can handle the get a good shape of the profile. And at last we applied the new equation of state Riemann solver to a light curve problem of the Mira variables. Thank you. And I want to thank these people.
Okay, so we had some questions throughout, but we have some time for more questions.
So I would imagine that when you have low density gas, then it could be the case that you're radiation dominated, right? In which case the phase transition are not going to be important, right? Because most of the energy is going to be in photons.
You need to be careful when you are talking about the radiation energy, because radiation energy is calculated through the radiative transfer equation. I, the intensity, you need to integrate over the all the angle, solid angle. But this intensity I, because gas is boson, this I, they can just, if you live far away from the star, this I just drop.
If you have a gas in a box and you wait for an infinite amount of time, wait for equilibrium, which is right? Then it could be the case when you make, especially when
That's not necessary. That low density gas does not necessarily have high radiation pressure. Even your temperature is high. Even your temperature is high. Yeah, that's true. If radiation and the gas is in equilibrium, but outside the photosphere, it may not be in equilibrium. The radiation and gas doesn't together in equilibrium. That's the optically thin regime. Your radiation is diluting, if in a metaphor.
I have a very basic question. So as somebody who does extremely simple binary evolution models, I'm curious how long the simulations that you showed us took.
Thank you for bringing up this question. If you are using, you are talking about using the realistic equation of state,
yeah.
Right? Okay, then with the analytic equation of state Riemann solver, its speed is 20 times as slow as the original HLC. However, 20 times is only in the hydro step. In a real multi-physics calculation, like if you need to solve self-gravity, if you need to solve radiation transfer, self-gravity is boson solver, radiation transfer, they all take a lot of time. Compared to that, the hydro step is still a fraction. It's not taking, even after multiplication of 20, it's not taking 90% of the computational time. Yeah.
Let's thank Zhuo one more time.